Okay, increasingly spicy ice tables here. Let's see what the new thing is. And there is a new thing with this one. This is a layout that we haven't seen before. We have sulfur trioxide reacting with nitrogen monoxide to make nitrogen dioxide and sulfur dioxide. And we have initial change equilibrium. And what have they given us? They say the K is 0.5. We don't need that right now, but I'm sure we will in a bit. And they give us moles. How big is our container? Trap. If we're doing concentrations here, these numbers must be divided by 2. Concentration is number of moles divided by volume. So for the SO3, it's 0.3 divided by 2. And for nitrogen monoxide, it's 0.3 divided by 2. So stay on top of that. Don't get caught. Those are placed in a container. They don't mention any of the products being in the container, so it's probably safe to assume there weren't any. And they want the equilibrium concentration of the gas. Now, every other time we've done this, we've had a column where we knew 2 of the 3 values, and we could do some subtracting and figure out what the change was in that column, and then we could tear around and find all the other stuff. That has not happened here. So we need a new approach. And the new approach involves some algebra. The way we can set this up is we know a certain amount of SO3 is going to get used. I don't know how much. Let's just call it X. Now, in this case, it's nice. All of these species have coefficients of 1. So if they're all 1 to 1 to 1 to 1, that means these numbers are all the same. So we can say they're all X. Both of these went down by X, and the NO2 and SO2 went up by X. And from that, we can write equilibrium amounts. Now, they're not going to be all that nice because they're going to have X's in them, but it's better than not knowing anything. For this, we have 0.15 minus X. And same for the nitrogen monoxide. Here we had nothing, and then we built up X, so our new total is X, and here 0 plus X is X again. So we have all that, and we can write a K expression, which unfortunately will also have X's in it. The K for this is NO2 times SO2 divided by SO3 and NO. Okay, just products minus reactants, and I'm putting in these equilibrium amounts. I did that in one step to save a little bit of time, but this is our K, and we know this comes out to 0.5. So if we could solve this for X, we'd be golden. We'd suddenly know everything in here. Can we solve this for X? Looks a little unpleasant, but let's see what we can do with it. X times X, we can just write as X squared. That helps a bit. 0.15 minus X twice, we can write as 0.15 minus X all squared. That's another improvement. And then this comes out to 0.5. Okay, that's maybe slightly better. Both of these things are squared. Is there a way we could get that off there? Say yes. How do you unsquare something? The opposite of squaring something is you square root it. So if we square root our left side and square root our right side, because we have to do both sides, treat both sides the same way, what do we get out of that? Well, the square root takes the squares off of both of these. It unsquares the x and it unsquares the denominator too. So we get x over 0.15 minus x equals, and the square root of 0.5 is 0.707. Might want a couple more. 70711, I guess. Can we solve that for x? It takes a little algebra, but yeah, we can. We can multiply both sides by this denominator, 0.15 minus x. That gets us here. X equals 0.70711 0.15 minus x. Now this means the 0.70711 distributes through these brackets, so it's going to multiply both of these things. Gives us x equals 0.70711 times 0.15 is 0.10607 minus 0.70711x. Okay, so we did 0.707 times this number, there's the result, and we did 0.707 times x, there's the result. Almost there, hang on. We'd like to get all our x's together on one side. We have a 1x over here. This x means 1x. If we take these x's over to the left, they become positive. Or you could say we're adding this to both sides, and we get 1.70711x equals 0.10607. And then we divide both sides by 1.707. So 0.10607 divided by 1.70711 x equals 0.0621. So all of these numbers in the change row are 0.0621. I'm just going to put that in there. 0.0621, 0.0621. You get the idea. And now that we know that, we can go through our equilibrium equilibrium row, and fill those things in. Let's see. 150 minus 62 is going to be 0.0889. I think, let me check that. This would be a bad time for an arithmetic mistake. 0.879. 0.0879. This amount is the exact same. And these two, because we started at 0, are easy to work out also. 0.0621, 0.0621. So those are the equilibrium concentrations of each gas. A little bit grueling, I know, but this is about as difficult as we can make an ice table problem. We can give you none of the equilibrium amounts, and then you have to put an x in the x's in the change row. In this case, it was all x's. If there had been some coefficients up here, we might have had 2 x's or 3 x's. I think we'll see that in some future examples. But anyway, from that you get an equation you have to solve. That tells you x. And once you know x, you can rampage around your table and fill in all the missing pieces. Let's try a couple more. All right, minor wrinkle in this one. They haven't written the formula for us, but that's okay. We're tough. In the formation of hydrogen iodide, we use hydrogen and iodine. All right. Hydrogen plus iodine makes hydrogen iodide. That's balanced if I throw a 2 down right there. Okay, that's not so bad. 1 liter vessel, and they put 1 mole of hydrogen and 1 mole of iodine. So initial change, equilibrium, 1 mole, no HI at the beginning. And what will be the final concentration in the vessel when equilibrium is established? The equilibrium constant is 45.9. K equals 45.9. So, again, we don't have any equilibrium numbers to work off of, so it's time for the X trick again. A certain amount of hydrogen is going to react. I don't know how much, so we'll call it X. The amount of iodine must be exactly the same because they're in a 1-to-1 ratio. And the HI is always twice as big as either of these, so we'll call it 2X. So what does that give us for equilibrium amounts? We have 1 mole of hydrogen, we've used up X, so we're down to there. Exact same thing for iodine. And for HI, we started with none and we made 2X, so our total now is 2X. when we write an equilibrium expression, the K should be, what is it? I'll write out the whole thing. HI squared over hydrogen and iodine. The HI is 2x squared. The hydrogen is 1 minus x. Now the iodine is also 1 minus x, so I'm going to write 1 minus x to the second power. And we know that our K has to come out to 45.9 if we're at equilibrium. So there we are. Remember the thing with the squares and how we get rid of them? It's happening again. We can strip off both of these squares if we go square root for u, square root for u. This square root is helping because it's going to clean these squares off. I don't particularly want to do this one, but rule number 1 of algebra says thou shalt treat both sides of an equation the same way. So if I root the left side, I must root the right side. So this takes the squares off, leaving us with just 2x over just 1 minus x. And over here we get the square root of 45.9, which I don't know what my calculator does. It's 6.775. Okay, well, we can solve this easier if we clean up the denominators. So multiply both sides by 1 minus x. On this side, the 1 minus x's cancel out. And so here we get 2x equals 6.775 times 1. That's easy. And 6.775 times x is not too bad either. There we go. Now, if we segregate this, if we get all our x's to one side and all our plain old numbers to the other, we take this 6.775 over to the left and we end up with 8.775x, right? The 2 that were there originally plus 6.775 more that just arrived. And that equals 6.775. And then we divide both sides by 8.775. And we get 0.772. Now, none of the answers are actually 0.772. We have to take this number back up into our table and sub it in these various places. So our concentration of hydrogen is 1 minus 0.772, which is 0.228. Iodine, exact same math, exact same answer. And for HI, it's 2 times x, so 2 times 0.772, which is 1.544. So those are our equilibrium concentrations for everything. By the way, if you ever get to the end of one of these and you feel like you want to check your answer because you just spent all this time and it would be a bummer to have made a mistake, it's not too hard to check them. All you have to do is take these concentrations that you think are correct, put them into your K. If they work, it should come out to 45.9 or pretty close. So if we try that here, HI squared, here's the test. HI squared is 1.544 squared. The hydrogen is 0.228. The iodine is also 0.228. If you work that out, divided by 0.228, divided by 0.228, we're hoping to see 45.9 when we do this, and I got 45.859, etc., which, if I do it to 3 decimal places, does, or 3 sig digs, does round to 45.9, so that means yes, looking good. It's very hard to accidentally get the right K value, so if you get the right K, you can pretty much count on all your concentrations being correct. And if you don't get the K, it means something's gone wrong. Go refill the coffee cup and start troubleshooting. Let's see. Okay, well, it's a reaction. It's all liquids, so they're all going to be included in the K. And let's just write this out again. Ethanol reacts with propanoic acid. It's propanoic because it's got 3 carbons in it, and it's oic acid because it's got the carboxyl group on the tail end. C2H5, COO, that's ethyl propanoate or ethyl propanoate. C2H5 and water. Okay, and we have probably, I haven't looked at the question yet, I'm just kind of automatically setting this up because I can see there are a lot of numbers getting thrown around here and we need somewhere to organize them or they will overwhelm us. Okay, 7.71 moles of ethanol are reacted in a beaker. 4.8 moles of ethyl propanoate are present when equilibrium is established, and the total volume of liquid is exactly 1 liter. So in other words, we're in a 1 liter container. Okay, that's good. That means we can trust these numbers. The concentrations are going to be 7.71 divided by 1, etc. So, hooray, it's a 1 liter system. So they say we start with 7.71 of ethanol and 737 of propanoic acid. And they say just those things are reacted in beakers, so I conclude there were none of these before the reaction began. And when the dust settles, we have 4.8 moles per liter of ethyl propanoate over here. Equilibrium amount 4.8. All right, and then what the K? Can we do this? It's actually not as bad as it looks because notice these are all 1 to 1. When we start filling in numbers, it's going to go quick. We started with none of this. We ended up with 4.8, so clearly we created 4.8 of it. Since these are all 1 to 1 ratios, that means all of these numbers are the same. They're all 4.8. We started with no water. We made 4.8. We must have 4.8 moles per liter of water now. We started with 737 of propanoic acid. We used up 4.8, so that takes us down to 2.57. And for this, 7.71, 2.91. I'm going to double check that. 771 minus 4.8. Yeah, 2.91. Okay, good. So that looked horrible, but finding the equilibrium amounts actually turned out to be no big deal. It was nice that it was 1 to 1. And now that we have the equilibrium amounts, we can work out a K. The K is our products over our reactants. I'm not going to write the equilibrium law because I don't want to write all these annoying big formulae. I'm just going to jump straight into putting the concentrations in. So for our products, we have 4.8 times another 4.8. And downstairs, our reactants, we have 291 and 257. Okay. 4.8 squared divided by 2.91, also divided by 2.57. I find that the equilibrium constant is 3.0807. How many sig digs are we keeping? 3, 3, 3. Is everything 3? Yeah. They're all 3, so 3.08 should do it for our constant. Okay, now what have we got? Carbon monoxide reacts with 2 hydrogen molecules to make methanol or methyl hydrate or wood alcohol. And they say the equilibrium constant is 0.5. And here come a bunch of concentrations, so let's make sure they have somewhere to go. A reaction mixture at equilibrium contains 0.12 of carbon monoxide, that's the equilibrium amount, and 0.1 moles per liter of hydrogen. And we don't know the methanol. I'll put an X. Question mark is understandable, but we should be putting X's. It's not like we've never seen algebra before. They want this amount at equilibrium. Well, we can write a K expression. We've got values for all of our concentrations, so we can say the K for this thing is the methanol concentration divided by the carbon monoxide concentration and the hydrogen concentration squared, because it's got a coefficient of 2. Notice these are all gases, so they are all included in the K. I hope you're keeping an eye on that. So if we put numbers into this, or values into this, for CH3OH, sadly, we get X. For carbon monoxide, we get 0.12. Hydrogen, we get 0.1. And all that equals 0.5. So X over 0.012 equals 0.5. What we have here is X divided by 0.012. If you want to clear that out, it's easy to do. You multiply both sides by 0.012. 0.012. These cancel out, leaving us with just X, which is nice. And on the other side, we get 0.5 times 0.012, which is 0.006. 0.006 moles per liter should be our equilibrium concentration for methanol.